Thank you. Thanks for the introduction and the warm words. And let us just dig in there. So basically what we want to do is we want to talk about this whole demo testbed that we built, and just having some kind of small introduction. You will see our showcase. We will talk about some other things we built on top already, as well as speaking about the reference architecture that we had in mind when building some things, as well as sharing with you our lessons learned, as well as having some Q&A session afterwards. That would be great. Cool, we're having technical problems, so that's as always in every good presentation, because then we are way more relaxed. Thank you. Awesome. Okay, maybe just 1 or 2 sentences to myself. So my name is Andre. I'm working in Accenture in the so-called Liquid Studio, and I'm basically focusing on IoT things, and I'm the so-called IoT tribe lead in Germany, in Austria. And yeah, by passion, I'm an interaction designer. You see, I'm a family guy. So over the day, I work for Accenture, and I'm there for my family. And you also see in the night, I'm there up there in my sound studio and doing drum and bass and some kind of dark techno. In case you're interested, and you can scan the QR code to listen to my Spotify. And yeah, then if I'm not sleeping at all and I still find time, I have some interest as well. Like here, I'm building some kind of ROS-based RC buggy, and yeah, too many topics I'm working on in parallel. But maybe, Roman, I just always ask myself who you are. Maybe you want to introduce yourself.
Yeah, thank you, Andre. So my name is Roman Oechslin. I'm a Swiss based in Zurich. I majored in robotics also in Switzerland. And you can see me on one of the pictures, you can see me working, and on the other one, you can see me laying around on the couch. So I guess I'll let you figure it out.
You're waiting for me, right, in this call?
Yeah, exactly. Yeah. So that's how we usually work with each other.
So we work together. Yeah.
Exactly. So I'm also part of the Liquid Studio together with Andre. And yeah, personally, I'm interested in learning languages. So it will be interesting to talk to you after this presentation as well. Maybe I might know the language Slovakian.
Cool. Let us be, but before Roman, before we get into detail, let us show the crowd what we're talking about. And so we prepared a very small, short video. Let me just play it. Hopefully the sound does not work. Let's see. I think I just have to press the play button. I think you have a sound compressor working against the audio stream from YouTube. Sorry, I'm sound guy, but it's not so important. And the music is anyhow not nice. It's not from me, so that's why. Heading over to the next one. No, not again. Please not. So actually, this is like the front end that we built, and you saw this kind of test bed with the robots driving around, and let us speak about this in a second, but this is like the front end, what you actually see. And maybe some of you guys have seen us already over there at the Accenture booth, and we were showing you how this whole showcase is working. And basically what you see here is just a very simple front end application, and I think this is interesting because I took a picture of the Linux desktop and put it to PowerPoint, and now you see this here, but we are streaming to YouTube. So this is kind of metaverse, Roman, or
right?
Yeah. But let us better not talk about things that we don't know. Let us maybe focus more on intelligent edge and cloud edge computing and what this really is about, right? So on the one hand, we were all brainwashed and said cloud is the future, and it's just cloud, and cloud is the best thing that you can do. But again, now there's a movement going back again to not on-premise, but we call it now edge computing. And edge computing is really focusing on some special things where you can have some benefits, like especially if you have some real-time data processing ongoing, and you always want to do the signal processing on the edge or next to the source of the location. I mean, NASA is doing the same thing basically with the robots they're sending around, right? And also if you have some latency sensitive applications, like in case of hard time, real-time requirements, for example, right? You want to do edge processing and not send the data to the cloud. I mean, I think everyone gets this. As well, if you maybe want to do something localized, and now I'm not really talking about privacy and data issues, for example, but there are many, many reasons to do the processing on the edge, so locally. But then on the other hand, right, we can't really deny that there are not any benefits from the cloud, right? Especially if you need massive storage of compute devices and as well storage, right? You maybe want to do some analysis where you put everything together. And there was a very interesting talk before from Ethan talking about data meshes, and this is also like, again, going into the future. But as well, if you have to consider the bandwidth issues, like where are your users located or how are your computing systems connected to each other, right? So it's always, you have to keep in mind, it's expensive to move back and forth or from one cloud provider to another one. But you see, there's also this horizontal axis. You have on the one hand speed and reliability and as well as privacy. So think about what you're going to use and what the application really would benefit from. But it's not always just binary. Yeah, there are cases where it makes sense to go fully into the cloud, maybe some partially on-premise or on the edge device. You have to think about what is the time criticality, for example, of your application? Where are your resources located? I think you get the idea. Just think about what you want to do. And we wanted to have a showcase to explain possible new clients, of course, how such solutions could look like. And basically, what we want to show is not just some small toy robots driving around, but really showcasing some kind of automated inspection. So you might have seen in the video here our nice little robot. This is called, it's a Turtlebot. You can buy this. We did not build this. You can just buy this easily. You have a Raspberry Pi in there, an OpenCR board controlling the servos and the stepper motors. You have a LiDAR sensor, a Raspi camera. So you can just buy this, and at the end of the day, you have a ROS-based robot that you can develop on your own. And this is really a nice platform.
A cool thing actually to add on the Turtlebot is that it's open source software and hardware.
Everything so open source. Yes.
It's made to customize, it's made to extend with your own components.
Yeah. And you also have seen maybe our nicely 3D printed nuclear waste disposal spill tons, because right, I am from Germany and there we have a problem with nuclear waste, right? We're thinking about where to put these things and just under the ground, and it should last there for millions of years. That's why we need robots that drive around and do inspection. So we're focusing on an automated inspection case that is super boring, so therefore we want to use robots. But of course, there are as well some other application areas. You can just think of different sites and plants, and very, like, especially some areas where you maybe don't want to have humans walking around. As well as we want to show some intelligent edge capabilities. So what we have here as well is this nice device from Amazon, from AWS. This is it's called an AWS Snow Cone, which is basically a computer with tons of terabytes of storage and a built-in Kindle display, which I think is cool. They did because they can, right? And we are using this for our edge processing. So in the end, you can run EC2 instances on that one. And this is a really cool thing because you can use the benefits of cloud deployment and your CI/CD pipeline maybe and just put this on this computing device, which is cool. So everything what you see AI inference related and heavily processing we are doing here on this edge device, while this robot is super simple, stupid and low power consumption based. So there's no proper intelligence and so on the robot to save battery power as well. And of course, we have to say, right, there are different industries. It's not just the nuclear waste disposal industries. So I think there are some forecasts, especially for utilities and retail and insurance-based scenarios where edge computing and robotics, especially this combination, is very interesting. And now you have seen a small video what we built. You have seen our front end, and what is happening there is just a slide about. So we imagine, like, the story is like, imagine from a plant manager, right? You have your waste disposal plant, and maybe you want to operate and drive there around manually. So you could do this with the front end if you have seen that. So you can drive around with this robot manually as well. There's a fully automated inspection. And after this inspection, the video is being uploaded to the edge device. And here we do our processing. And it detects whether there is some spill or not, and then we display it in the front end. That's basically all. And everything is, as I said already, everything is based around this edge computing device. So you have the robot operator, we have a user interface. It's connected to AWS, where you can have further analysis, for example, or maybe even different plants, right? As well as some databases and Just shortly about the showcase setup, right? You see we have some on-premise device, we have the cloud, we We have a GitLab repository, everything. We just integrated everything together. We have some databases. We are using AWS Greengrass. The motor control is basically done by ROS 2. So there's always an interesting discussion about ROS 1 versus ROS 2. But the interesting thing with ROS is that you can basically abstract your development of robotics. So once you have this robot, you maybe get used to how to develop for this one. But with ROS, you can put this into a simulator and maybe have 10 robots around or 100, and you can develop for this. And this is the nice thing about ROS. Before I'm heading over to you, Roman, for the reference architecture, in the end, this is like our blueprint. So if you want to recreate it, feel free. You see from left to the right on the Turtlebot, all the services and what is happening there. Then on the Edge Gateway, the same thing. We have some APIs and things are running here on this edge. And in the end, in AWS, we're using some buckets and some Elastic Cloud Computing. And the GitLab is also hosted as well, like our source code on AWS.
Spoiler alert, there's actually the security threat as well. You forgot about the
security. We need
most important thing, right?
Do we need security or?
I think it's Accenture. Maybe we can.
Yeah. Okay. Let's offer some security as well, because this is also a problem of ROS. Like, it's super open. Yeah. Once you're in the network of your subnet of your ROS devices, you can just overwrite the commands and send crazy commands so that the robot maybe drives your downside. Right. That would be really a pity. So therefore, our testbed is not just for us to show like how awesome we are and what we developed, but as well another team was developing some other showcases on top. For example, they want to show with secure ROS that somebody cannot modify this command velocity command that we're using to control the robot. Or they have a case, for example, right, there is an SD card. What about if you exchange the SD card and have some malicious software on there, like some other weird operating systems? Or maybe you can just connect a USB thumb flash drive to the Raspberry Pi and all these things. It's really not secured. And this is what they are going to showcase, what is possible and how to harden this and secure it, basically. But maybe, Roman, let us head over more to the reference architecture, because there's not just our small demo, but really more like a big picture, because this is the implementation and the first reference implementation of a reference architecture that we had in mind, that we especially can use for intelligent edge computing.
Yeah, thank you. Before we switch over to the immense picture that might hit some of you a bit too much in the face, because there's
those are typical Accenture slides. There's always too much text. So
a lot of components that are waiting for you here. So I'll just take one step back. Reference architecture is basically a template that we created. And the template should help you to design a similar project. Doesn't have to be the same, but it should help you and guide you to pick and cherry pick basically the right components for your application or for your project even. And now here's the full-fledged picture. So I think you know these kinds of slides. In the reference architecture, you want to capture as many components as possible. So what we analyzed here is various aspects, functional, also non-functional, the technical requirements, and the infrastructure itself, and then obviously the DevSecOps parts. What you can see here highlighted in violet or in purple is a subset of those components that are relevant for our use case with the Turtlebots. And I would like to just highlight a selected few of them, just to make it more easy to understand and to digest. So one of the subcomponents that you can see in the functional part is the digital twin. So we were focusing on having a digital representation of a real physical object, so that you can understand if you're interacting with this physical robots, then you have a digital twin of it. So you can see all the sensory input, you can see all the state of this robot, you can navigate it directly. So it's the real representation of this robot. Another thing is external perception. So it's equipped with many sensors, which gathers a lot of data. That's why also we decided to use the edge capability. And all these sensors, all those components need to be fused together into some intelligence. And this is done by real-time processing or also stream processing. So we're capable of doing both stream processing for the video feed, and then real-time processing with the analytics, that whenever we see one of those malicious leaks or of these dangerous leaks, that we can create alerts and also warn, for example, the warehouse manager that there's a problem on site. And last but not least, on the technical part, the very first component is HMI, so human-machine interface. It's quite an important, I see some people nodding already, it's quite an important aspect that shouldn't be forgotten. So the machine itself is basically useless if we cannot control it. So that's why we have to also focus on design, on how to operate it and how to interact with it. Do you want to add anything on this slide, or is it
maybe some useless comment like, did you know that font size 6 was invented for Accenture so that we can have this kind of text on it? I think nobody else is having so small fonts, but yeah, I think it tells a story, right? We have lots of things in there and people get an idea really what is happening here.
Actually, another thing that I would like to add is the localization part. So what is possible with ROS is to have a simultaneous localization and mapping, short SLAM. And this basically makes sure that the robot understands where it is located, in which room. So if you think about it, you probably know the Roomba vacuum cleaner. It might do this the same thing. So it understands where in the room it is, where the charging station is, and tries to more or less do an efficient route to clean up everything and not cover the same spot twice. With our sensors that we have here, we are capable of doing the same thing, easily implemented with ROS, so that you have a picture of the room itself and of where the robot is located. All right. After the implementation of the POC, or of our whole prototype and setup here, we learned a few things. We made a few conclusions on what is important, what is necessary, and I would like to cover a few points here. So one thing is the environment. We're dealing with physical robots, we're dealing with hardware. It's quite difficult to upload the new software to the robots because you have to be in the room. With COVID times, that's not always possible that you go to the office. So you have to update somehow the software. You have a human in the loop. It's a slow process. It's might even be error prone. So that's why we suggest that if you start your own project, try to virtualize your environment. Try to make those digital twins, make a simulation of your robot so that you can test as much as possible virtually. That you're not reliant on physical contact with the robot. Another thing is there is not one single edge. There are a lot of different edge devices. You have to think about which edge device you want to use. And for this, you have to understand the use case that you're dealing with. Obviously, we did that already in the beginning, and that's why we chose the snow cone. Unfortunately, that's not true, but we realized on the way that it's not the ideal setup to use for machine learning models, for example. So the one that we aimed for was not supported by the snow cone, so we had
to YOLO version,
yeah. So we even had to downgrade our YOLO version to lower version. And YOLO is not a joke, so it's really the model that is called YOLO. You only look once for the visual detection. So make sure that you understand the use case so that you can choose your hardware correspondingly. Then optimizing in real time means that whenever you deal with lots of sensors, with hardware, with robots, you want to get easy access to the data. You want to have some video feed. You want to see are the wheels turning or not. So make those custom scripts that you need in order to test whatever you implemented. And there are always some things that break. If you only touch the wheels, obviously the LiDAR will break as well. If you only touch the LiDAR, probably the battery explodes. So it's always a bit coupled. Another thing, rapid tech. So what we learned while using ROS1 is that there's another thing called ROS2. So obviously we jumped onto ROS2 because there were new features available. And then we realized, okay, the features that we implemented previously were now no longer supported with ROS2. So it basically broke our running system. That's why we had to downgrade again to ROS1 to make sure that the basic use case that we wanted to look at was still covered. And the ROS2 is still is open source, still being contributed on a regular basis, and that's why it's also very, very dynamic, which means that you can have the latest features maybe even next week, but not today. So that's a big point to take into consideration as well. Then I would like to cover the connectivity and 5G implementation at the same time. So we tried to connect everything locally with a 5G subnet, a 5G network, but we realized that with the hardware that we have, we had some troubles connecting every single item. So here the snow cone and the Raspberry Pi or the Turtlebot with an attached 5G modem, which didn't work as we planned, so we had to cross that off our features list and just say, okay, we'll leave it for a future implementation. If anyone is willing to pick it up, then please take the 5G. Another thing is the industrialization. We used this Turtlebot specifically because it's off the shelf, but you can customize it. And this is an easy to work with and an easy to start basis that allows for quite a flexible setup for different use cases. And then last but not least, the Edge maturity. So Edge is relatively new. There are some things that will change, and you just have to take that into account, that it's not a perfect setup. It's not a system that has been here for years. You have to get used to it. You have to work with limited documentation or tests even. All right, so this is the retrospective of our robot implementation, and basically what we learned from these lessons is point number one: virtualized environments. We took that point as input for our next projects, and that's basically also the outlook that we want to treat now. So the next projects that we dealt with after this robotics implementation was a robotics simulator, which I would like to quickly show in a video. All right, so this is a robotics simulator. This means that this is the virtualized environment that I was talking about earlier. So we built that as well as a conclusion of our previous implementation. And what you can see here is a Unity implementation of our little Turtlebot here. And you can use it for maintenance. You can use it for testing your control software. You can use it for any kind of changes that you would like to make to your robots. And now we're switching over to the serial robot, so a panda arm with several different joints. The question would be, okay, if I change my software now, does it still behave like I expect it to? And here we can see that we deployed everything to RoboMaker so that it's running online on the AWS cloud. You don't need to have a super fancy computer to run it with Unity. And you make use of the nice physics engine, but you can just deploy it and it runs it for you. And an interesting thing about, for example, the serial robot is you can control it in target state mode, for example, or in direct control. So the question is, do you want to directly control your robot in your lab, for example, and see how it's behaving in the simulation, get some sensor data, or if you're deploying a new version, for example, you just want to check out, okay, what would be the target state of this robot, and is it possible to reach it safely? And before you want to risk your hardware and risk your robot, you want to see the trajectory so that it reaches the target state.
But this you played.
Yeah, I'll jump to the relevant part. You see in blue is the shadow. This will be the target state. You can modify it to reach it. And then in white and in the bottom, you see the real robot in the lab, which then really follows that trajectory. So this is the robotics simulator that we built. And it's built for extensibility. It's built for being built upon and used as a basis. So you can configure new robots, can be serial. You can configure your own setup of the robotics, of the robot arm, for example, and use it as a test bed, as a test framework for yourself. Now, again, there's a bit of text. I think we covered most of the parts here. I think the interesting part is just really the shadow. So the simulation engine also provides you additional sensor input, which can be quite useful if you want to deal with not real, but realistic sensor input. So you cannot always gather all the data from the real lab, but you somehow have to use the realistic sensory input with real world like noise, so that you don't have always perfect information, for example. Anything to add from your side?
No,
just too much text already?
But I think people get the point, right? That this is a kind of journey that we're doing with robotics and also educating in ourselves and leveling up with things. And I think it's very interesting. That's why we're here, right? No, but just head over.
Okay. Then the next project, I'll start it here. This time with sound again, but I'll cover it with my voiceover. So this was a robothon, a hackathon with robotics organized by the Technical University in Munich. Don't worry about the text, I'll cover the details with my voice. So the target of this robothon was to tackle industrial robotization of dealing and disassembling electronic waste. So if you have a lot of waste that might be difficult or dangerous to disassemble or even expensive to disassemble manually, that's why they created this challenge to tackle individual tasks. And there were 4 tasks in total, and you will see it on the video which tasks there were tackled. Here you can see the team that was applying for this robotics challenge. So here they realized that touching a button is actually quite a difficult task. So that's why with the gripper you saw that they first tried to grip an object and then touch the button with the object. And here you have to check out with which precision they're able to do that. Usually when I get home, I try 5 or 6 times to then manage what the robot is doing here.
Or like the USB thumb, right? You always need 3 attempts to have it right.
Sure.
This is the Ethernet jack. Yeah, that's the end of the video and also already the end of the presentation. If I skip the next Accenture slide with a lot of text where it's just summing up again what we've seen. One of the key features here is that it had to orient itself and it had to find the task board here, the black thing, with the camera that is on the robot. So it's also a noisy environment that it's not always exactly aligned straight to the robot, but you have to find the task board first and then reference from there. That's why, for example, the press of the button was that difficult, because we just had to find the button first and hit it. Yeah, and now we head over to the Q&A. Please ask us some questions, but not too difficult. Otherwise, it will be embarrassing that they realize that we didn't do all the robots ourselves. Oh, I read them? Okay. So the first question is anonymous, and it says, why to develop your own simulator? Gazebo was enough. Why? Was not enough. Why? So one thing, I'm not a Gazebo expert, but what we realized with different vendors and their simulators, so with several different robotics vendors, you have
and a specific implementation for a simulation. And the problem there was that it's a vendor lock-in, right? So your vendor specific. Okay, so Gazebo is part of the ROS operating system, someone says from the audience. Yeah.
But you mean this compared to Unity? Yeah, sure. But you can also say Unity, for example, has way different features, different feature set, right? And for example, especially with Unity, you can make it as well, not just way more attractive, but as well, I think there are more Unity developers out there, at least I know personally, than Gazebo engineers, maybe, at least in my opinion. But of course, that's not it's not binary, right? It's not. I'm not saying that this is the best thing, but then again, from Unity, you might have as well some other connections. Let's say, for example, what about handicapped persons, for example, right? And all those things are covered if you head over to a big ecoverse like Unity, if you ask me.
Then the next question is, did you try to use cloud services, example, for image recognition? If yes, was it fast enough and real time?
You want to cover?
You can go first.
So in my opinion, yes. So first, yes, we did. And we have several projects where, of course, we also do our inference in the cloud, which works and can scale up to a certain point. But why in this case we were doing the inference on the edge is just because of scale factors. Yeah. So think about all these robots. Let's say we have hundreds, and then we say, okay, we have maybe a bigger device, like a bigger, let's say 40,000 AI GPU machine can handle all these things and so on. But streaming these hundreds of devices into the cloud, right? The costs would explode. So therefore, this doesn't make sense from an architecture point of view. Then again, okay, our case was not really. Now again, I'm heading over here to the bots. The case was not really real-time sensitive because the robot can drive around and send the video then to the edge device, and we can do our batch processing there. Just want to detect something, so there we have all the time to do the processing, so it makes sense to do this on the edge, but it does not make sense to stream it into the cloud because then we have some other connectivity. Instead, the better choice was to just send the metadata, like the result, into the cloud where you have the analytics.
In addition to that, the first decision was to focus on the use case with this atomic waste. And we assumed that if you're shut off from the outside world and don't have internet connectivity, then you're not directly connected to the cloud. So that's why we basically also said that, okay, we don't want to rely on cloud services, but want to showcase also the AI capability from Accenture and use our own models to train the image recognition, for example.
Additionally, we are in Germany and there's internet not always available, so we have to deal with being offline and still have to do mission critical analysis. Thanks.
All right, there's another question. Why haven't you used PIT controller to smooth out movement of the robots? So the control was done by ROS directly. So I'm not sure what the actual implementation is. Probably there is a PID control. One thing that we realized is based on the, so usually we tested with a predefined path, and this you can just record by ROS. Now it's getting a bit technical, but the question I think is
but that's why we're here, Roman.
Exactly. Yeah. So imagine that I record the path of the robot, I drive it manually, then I record all the commands. So like if I had a remote control in my hands, I'm recording all the commands, and then I can replay them all the time. And what we realized is that sometimes those messages get dropped, or some of the messages get dropped, and that's why it looks a bit shaky. That's one point. And the second point, so that might be what you saw earlier today in the test demo or in the exhibition site. The other point is that maybe also on the video it looked a bit more shaky than it even was when we drove it around in direct control. So if you just give the velocity commands, then ROS usually takes care of feeding the motors, of controlling them so that it matches the target speed that you set. I see that there are a lot of questions dropping in. I would like to start learning robot programming. Which platform do you suggest?
ROS
Less
2.
than $3,000.
And take such Turtlebot. They're really nice. They're not too expensive. You can enhance them. We're really convinced by them. I mean, you can easily just attach your own sensors, like a distance sensor, for example, right? Or whatever. It comes with an inbuilt LiDAR sensor already, which is, I think, quite crazy. And also, which is, I think, another argument for this, it's Raspberry Pi based. So I think the community for Raspberry Pis, right, is quite open, and you can do many things with that. So I would go for that if you want to really have hands-on. Like maybe you saw on my picture when I was introducing myself there, I have my RC buggy and trying to do everything on my own, but it's really a pity. It's really difficult to start somewhere. And here, I promise you, at the end of the day, you have a robot driving around with your WASD keys, which I think is nice. And then based on this, you can continue.
And you're still far below from the $3,000. So for our special tip, please, the rest could be donated to some good purpose. But you're really not even close to the 3,000. So yeah, go for the Turtlebots, go for ROS. That's a good starting point. All right, that's all the questions and all the answers. So thanks a lot for listening to us, and thanks for laughing at the jokes.